March 15, 1944. 15,000 feet up above the rolling English countryside. Captain Francis Gabresky eases his throttle forward and reaches for the water injection switch, throwing it to emergency power. His brand new P-47 Thunderbolt, fitted with the latest advancement that promised to transform his engine from 2,000 horsepower into a blazing 2,500, suddenly lurches. The engine coughs and begins to fail. Below him, German fighters slip away into the distance as he struggles to nurse his crippled aircraft back toward home. Across every 8th Air Force base scattered throughout England, other pilots are living through the identical nightmare. This advanced fuel injection system was meant to give American pilots the edge they desperately needed. Instead, it's destroying engines. Manifold pressure readings plummet. Cylinders start cracking. Pilots are dying. Military experts across the board insist the problem runs deep into the fundamentals. You cannot simply force an air-cooled engine past what it was designed to handle without causing catastrophic breakdown. The laws of nature have their limits. Yet in a laboratory in Connecticut, a junior engineer named Frank Walker studies his test results and realizes something doesn't add up. The alcohol mixture that everyone has been using doesn't stop engine knock at all. The data shows it actually causes the problem. Walker's numbers point to something that seems impossible. A completely different fuel formula that might produce 40% more power without changing the engine itself. The experts call it madness. Walker calls it science. And buried between these two opposing views exists the answer that would let American fighters do what everyone thought was impossible. What every German strategist believed violated the laws of physics itself. The Rolls-Royce Merlin engines of the Mustang escort fighters had already vanished into tiny specks when Captain Francis Gabresky felt the first shudder run through his control stick. 15,000 feet above the patchwork landscape of Cambridgeshire, his P-47 D-10 Thunderbolt held formation with 11 other Republic fighters. Their massive radial engines pulling through the thin March air at 2,700 revolutions per minute. The manifold pressure gauge showed 52 inches of mercury, exactly right for cruise power in the R-2800 double wasp that filled the fighter's nose like some kind of mechanical beating heart. Gabresky had been flying the jug for 8 months now, racking up victories against the Luftwaffe's finest pilots. But this particular airplane was something special. Straight from the factory at Republic Aviation's Farmingdale plant, it carried the newest modification that ground crews talked about with almost reverent whispers: anti-detonation injection, water injection. The miracle system that could turn his capable but heavy fighter into something approaching the agility and speed of German interceptors. The radar station at Dover had given them vectors toward a formation of Messerschmitt Bf-109s, climbing up out of France, roughly 30 miles southeast and closing in. At this altitude, the German fighters held every advantage. They were lighter, more nimble, with engines tuned specifically for thin air operations. But today, Gabresky carried something the Luftwaffe had never come up against. He reached down toward the toggle switch on his throttle quadrant, the one connected to the pressurized tank behind his seat, holding 15 gallons of isopropyl alcohol mixed with distilled water. Republic's engineers had walked him through the whole theory during his transition briefing. Inject this mixture into the supercharger intake when running at high power, and the R-2800 would produce 2,530 horsepower instead of the normal 2,000. 30% more power, the difference between chasing German fighters and actually catching them. The 109s appeared first as flashes of sunlight bouncing off metal, then as clear shapes with their distinctive elliptical wings and angular tails. Gabresky shoved his throttle all the way forward and flipped the water injection switch. The system should have kicked in automatically once manifold pressure topped 54 inches, spraying the supercharger with alcohol and water to stop the rough combustion that came with emergency power. Instead, the double wasp gasped like a dying animal. The manifold pressure gauge that should have climbed steadily up to 65 inches started wavering and dropping instead. Engine temperature shot up beyond what it should be. Through the metal floor of the cockpit, Gabresky could feel violent shaking coming from somewhere deep inside the engine's 18 cylinders. The RPM started falling even though his throttle was all the way forward. Even worse, the high-pitched whine of the supercharger turned into a broken, stuttering sound. Below him, Lieutenant Bob Johnson's Thunderbolt was experiencing the exact same thing. Johnson, who usually went after German fighters with fierce determination, was backing off his throttle and making wild gestures toward his instruments. All through the formation, other P-47 pilots were discovering the same terrible truth. The system that was supposed to give them the winning advantage was actually taking power away exactly when they needed it most. The Messerschmitts, seeing the Americans struggling, attacked harder with the confidence of hunters who smell blood. Their Daimler-Benz 605 engines, producing 1,700 horsepower through normal operation, suddenly looked incredibly powerful compared to Thunderbolts now putting out only 1,600, less than what they produced normally. Gabresky coaxed his damaged fighter through a climbing turn, helpless as German fighters tore through his formation. The whole situation had flipped upside down. Instead of using extra power to control the fight, the Americans were just trying to survive with broken aircraft. Two more Thunderbolts started losing power, their pilots sending frantic messages about engines running rough and pressure gauges falling. The entire fight lasted 12 minutes. When it ended, the Luftwaffe had gotten away without suffering a single loss, while 3 P-47s limped home on reduced power, their water injection systems turned off, their engines coughing and sputtering randomly. Gabresky managed to coax his Thunderbolt back down to RAF Steeple Morden by keeping the throttle low, listening to the broken rhythm of cylinders no longer firing properly. On the ground, Master Sergeant Mike Quirk opened up Gabresky's engine to take a look, and what he found made everything clear. Cylinder number 14 showed terrible detonation damage, the kind of self-combustion that would wreck an engine in minutes. The spark plugs were eaten away, the cylinder head had stress cracks, and dark powder coated the intake valves. This wasn't just random mechanical failure. This was planned destruction happening systematically. Within hours, the reports started coming in from 8th Air Force fighter bases all over the place. At Boxted, Debden and Lisden, maintenance crews were pulling cylinders from brand-new P-47 D-10s that had gotten the water injection upgrade. The damage pattern was identical in every case. Engage the ADI at high power, and the engine destroys itself from within. Colonel Hubert Zemk, commanding the 56th Fighter Group, shut down his entire squadron pending an investigation. At Debden, the 4th Fighter Group did the same thing. By that evening, nearly 200 of the Army Air Force's most advanced fighters sat quiet on their concrete stands. Their revolutionary power systems declared unfit for flying combat. In his report after landing, Gabresky wrote with precise detail, "Water injection system caused severe engine roughness and power loss at 63 inches manifold pressure. System appears to cause rather than prevent detonation. Recommend immediate investigation." He didn't write down his private worry that somewhere in the design process, from Republic Aviation's drawing boards through Pratt and Whitney's factories, a serious mistake had turned their greatest technical advantage into possibly their worst weakness. The miracle that was supposed to make American fighters beat physics had instead made them weaker than German fighters using basic technology. No one could explain why. The emergency meeting at Wright-Patterson Army Airfield started at 8 in the morning on March the 20th. Every organization involved in American fighter engine development sent representatives. Colonel Benjamin Chidlaw, running the Fighter Projects Office, sat at the head of a mahogany table with the finest aeronautical engineers in America arranged around him. To his left, Leonard Hobbs from Wright Aeronautical spread technical drawings across the polished wood. To his right, senior Pratt and Whitney engineers arranged thick folders filled with test results and reports of failures. The answer became obvious within minutes, settling in like concrete hardening in cold weather. Dr. Samuel Heron, a British combustion specialist whose research shaped American engine development over the past 20 years, spoke with the certainty of accumulated knowledge. The R2800 double wasp, he explained, was already running at the absolute edge of what materials science and thermodynamic physics allowed. 18 cylinders, displacing 2,804 cubic inches, spinning at 2,700 RPM, pulling out 2,000 horsepower from air-cooled aluminum and steel. This represented the absolute top of what piston engines could achieve. The math didn't lie. Compression ratio stayed at 6.65 to 1. Cylinder head temperatures that couldn't go above 500 degrees Fahrenheit, or the aluminum castings would warp. Manifold pressure capped at 52 inches of mercury to stop detonation, that sudden self-ignition. These weren't just arbitrary limits someone decided on. They were absolute physical laws, as binding as gravity or the laws of thermodynamics. Major Harold Neely from Wright Aeronautical presented the failure data that backed up every single assumption. The destroyed cylinders from England showed classic detonation patterns. Electrodes burned away by temperatures past 3,000 degrees. Aluminum pistons with holes punched clean through. Cylinder walls scored by fragments of metal traveling faster than sound. This was what happened when engineers tried to push past what nature permitted. This was what happened when wartime desperation drove technology past what made sense. The officers in charge nodded, pleased that their careful approach had been proven right. Colonel Robert Harper from Material Command had been fundamentally opposed to the water injection program from the very beginning. His objection was straightforward and rooted in practical military experience. Field modifications, he argued, introduced too many unpredictable variables into systems that demanded absolute reliability. Combat aircraft needed engines that had been proven through countless hours of rigorous testing, not experimental modifications hastily developed under the pressure of wartime deadlines. The engine failures that occurred in England provided irrefutable evidence that his concerns had been justified. Leonard Hobbs carefully unrolled a detailed cross-sectional drawing of the R-2800's combustion chamber, using his finger to trace exactly where the problem originated. The process was straightforward in theory. Fuel and air entered through intake valves while aluminum pistons compressed the mixture as they rose inside steel cylinders. Precisely timed spark plugs ignited everything at exactly the right moment. Under normal operating conditions, combustion spread smoothly outward from the spark plug in a controlled expanding flame. But push the pressure and temperature beyond what the engine was designed to handle, and something catastrophic happened. Spontaneous ignition occurred simultaneously throughout the entire fuel mixture instead of the orderly, controlled expansion that pushed the piston downward. Instead, violent explosion hammered the piston with forces that no mechanical system could possibly survive. The isopropyl alcohol mixture being used in the water injection system carried an octane rating of 118, which exceeded aviation gasoline and theoretically should have been sufficient to prevent early ignition. Yet theory and reality diverged sharply when aluminum castings heated far beyond their design specifications and compression ratios crept dangerously close to the detonation threshold. The alcohol simply could not overcome the fundamental physics governing internal combustion engines. Dr. Heron drove home the mathematical certainty with numbers that admitted no argument. At maximum power output, cylinder pressure reached 800 pounds per square inch. Inside the combustion chamber, temperature climbed to 2,200 degrees Fahrenheit. Heat rejection through the cylinder cooling fins amounted to 42,000 BTUs per hour. These figures represented the absolute performance ceiling for air-cooled engine design, established through decades of accumulated research and validated by thousands upon thousands of hours of operational testing. The younger engineers from Pratt & Whitney, including men like Bill Klaus and the junior chemist Frank Walker, found themselves listening with increasing frustration as senior experts methodically dismantled every possibility for a technical solution. Walker had presented preliminary research suggesting that different alcohol formulations might perform in unexpected ways under extreme conditions. The senior engineers dismissed his work as pure laboratory speculation, completely disconnected from real engineering reality. Methanol and ethanol might display promising characteristics within controlled test conditions, yet field operations demanded materials that were proven, reliable, and readily obtainable. Colonel Harper laid out the procurement logic with devastating efficiency. Isopropyl alcohol was already manufactured in substantial quantities by pharmaceutical companies and flowed through established supply chains. It worked with rubber seals and aluminum fittings throughout the injection system without corrosion or compatibility issues. Switching to alternative alcohols would require months of additional testing. establishing new production contracts, modifying storage and handling procedures, and retraining every maintenance crew. The war would continue regardless of whether engineers pursued theoretical refinements. The meeting concluded with universal agreement that the water injection program should be abandoned, pending a complete redesign from the ground up. The R-2800 would revert to its thoroughly proven 2,000 horsepower rating with conventional fuel systems. American fighters would accept their performance disadvantage rather than gamble with catastrophic mechanical failure during combat operations. As people collected their papers and prepared to leave, Frank Walker remained at the table, absorbed in data that every other person had rejected. His laboratory tests showed octane ratings that contradicted the accepted understanding. Methanol registered 133, ethanol came in at 129, and water itself possessed an infinite octane rating because water could not burn at all. Yet these numbers meant nothing unless they could be converted into engines that functioned properly during actual combat. The collective wisdom had spoken with undeniable authority. Physics established boundaries that engineering could not transcend, and rational design practice meant respecting those boundaries rather than attempting to overcome them. The water injection system would be shelved, American fighters would continue fighting at a disadvantage, and the war would proceed using technologies that functioned reliably, even if not optimally. Walker closed his notebook, understanding that mathematical certainty sometimes diverged from engineering reality in ways that senior experts failed to recognize. Bill Klaus arrived at RAF Steeple Morden on March 28, carrying nothing except a single canvas bag and a resolve that approached outright insubordination. The official order from Wright-Patterson had been crystal clear: suspend all water injection testing and restore every P-47 to standard configuration. Yet during his Atlantic crossing, Klaus had devoted himself to studying Frank Walker's laboratory data, and the numbers suggested possibilities that contradicted everything he had heard from expert voices. Master Sergeant Mike Quirk met him at the flight line where Gabresky's damaged Thunderbolt sat stripped of its cowling panels, exposing the injured R-2800 like a patient prepped for surgery. Quirk possessed decades of experience maintaining radial engines stretching back before Pearl Harbor, and his experienced eye could interpret mechanical distress from the arrangement of carbon deposits and metal patterns. This particular engine bore testimony to violence, cylinders that had been pounded by explosions rather than propelled by controlled combustion. Klaus examined the destroyed parts with deliberate precision, approaching the work like someone investigating a crime scene. Piston number 14 displayed a hole burned completely through its aluminum top. The intake valve had warped far beyond acceptable limits. Carbon deposits covered areas that should have remained pristine, but most revealing were the spark plug electrodes, worn into jagged, irregular shapes that showed temperatures far surpassing normal combustion limits. Walker's hypothesis concentrated on molecular behavior occurring faster than conscious human awareness. During the brief milliseconds between spark ignition and piston movement, alcohol molecules fractured under extraordinary temperature and pressure. Isopropyl alcohol, the approved formulation, degraded into compounds that actually encouraged spontaneous combustion instead of preventing it. But methanol and ethanol reacted differently, maintaining their anti-detonation characteristics even inside the brutal conditions within a combat-loaded R-2800. The difficulty lay in validating this hypothesis without official endorsement or sufficient testing capacity. Klaus persuaded Quirk to ready a single P-47 for secret trials, using maintenance steps that looked completely normal, while actually employing Walker's unconventional chemistry. They emptied the isopropyl alcohol mixture from the injection tank and refilled it with methanol they obtained from Cambridge Chemical Supply Company, blending it 50-50 with purified water. Lieutenant Colonel Francis Gabresky volunteered his aircraft for the unauthorized experiment, despite direct orders prohibiting the water injection system. His reason was deeply personal. German fighters had gotten away during the March 15th combat engagement specifically because his Thunderbolt lacked sufficient power for an effective pursuit. If Walker's formula could restore that performance edge, Gabresky felt willing to face court-martial. The ground test produced results that contradicted every assumption. Where isopropyl alcohol had created rough running and lost power, the methanol mixture generated smooth acceleration across the entire performance envelope. Engine temperatures remained inside normal ranges, even at 65 inches of manifold pressure. Most strikingly, the characteristic whine of the turbo supercharger sustained its steady tone rather than fracturing into the jagged rasp, signaling mechanical failure. Klaus observed the engine gauges while Quirk regulated fuel supply and injection timing. Manifold pressure increased steadily from 52 inches to 65 inches without the stuttering that had plagued earlier attempts. Cylinder head temperatures, instead of skyrocketing past safe levels, actually fell as the methanol water formula absorbed combustion energy and prevented the concentrated heat zones that triggered detonation. The pivotal moment happened during a high-power engine test that would have wrecked the engine with isopropyl alcohol injection. Gabresky moved the throttle to maximum emergency position, 68 inches of manifold pressure at 2800 RPM. The R2800 responded with raw authority, generating 2800 horsepower instead of the standard 2000. Through the headphones, Klaus heard the powerful roar of an engine exceeding its rated output without mechanical damage. The performance figures confirmed Walker's most ambitious expectations. Climb rate jumped from 2,800 feet per minute to 3,800 feet per minute. Time to reach 15,000 feet fell from 6.2 minutes to 4.1 minutes. Most crucially, top speed at 25,000 feet climbed from 425 miles per hour to 465 miles per hour, faster than any German aircraft at the same altitude. News of the successful tests circulated through the 56th Fighter Group at the speed of classified information that somehow everyone needed to know. Squadron leaders who had watched their pilots struggle with underpowered fighters suddenly glimpsed the possibility of technical superiority over the Luftwaffe. But adopting Walker's formula meant sidestepping official procedures and risking personal careers on untested chemistry. Major David Schilling, the group's most accomplished test pilot, persuaded Colonel Zemke to authorize a single demonstration flight employing the modified injection system. On April 3rd, Schilling flew Gabresky's Thunderbolt to 30,000 feet and switched on the water injection during a high-speed run designed to validate or refute Walker's theory under conditions mimicking combat maneuvering. The performance surpassed every projection. Schilling's P-47 accelerated from 400 miles per hour to 480 miles per hour in level flight, then powered upward without the engine roughness that had plagued isopropyl alcohol tests. Controllers on the ground tracking the aircraft reported speed readings that appeared impossible. A Thunderbolt sustaining 465 miles per hour at 28,000 feet while climbing at over 3,000 feet per minute. Schilling's voice came through the radio crackling with enthusiasm that broke through his normally composed demeanor. "This thing climbs like a rocket and runs like a scalded cat." Whatever Walker mixed together, it turned the jug into a completely different machine. The flight data confirmed performance gains that converted the P-47 from a strong but heavy interceptor into a fighter capable of dominating any adversary through superior power and climb capability. By evening, mechanics across the 56th Fighter Group were quietly draining isopropyl alcohol from injection tanks and restocking them with Walker's methanol formula. The changeover occurred without official authorization, formal documentation, or administrative oversight. A grassroots technical revolution driven by combat reality rather than bureaucratic channels. Frank Walker's chemistry had validated itself where it mattered most, in the three-dimensional world of aerial combat, where small performance margins measured the difference between victory and defeat, between returning home and not coming back. Colonel Hubert Zemke reached a decision that could either vindicate Frank Walker's chemistry or devastate the most accomplished fighter unit in the European theater. On April 7, 1944, he authorized the conversion of every P-47 in the 56th Fighter Group to the unauthorized methanol water formula, gambling 48 aircraft and their pilots on the calculations of a junior chemist operating 3,000 miles away. The logistics required deception approaching mutiny. Master sergeants throughout the group coordinated their actions like people planning a conspiracy. draining approved isopropyl alcohol from injection tanks during regular maintenance and refilling them with methanol obtained through civilian distributors. Official technical orders got ignored, standard procurement procedures got bypassed, quality control inspections happened with mechanics deliberately overlooking the violations. Captain Robert Johnson grasped the risk as he walked around his P-47 performing the pre-flight check on April 8th. If Walker's mixture failed during combat, the engine would destroy itself precisely when maximum power became absolutely essential. During emergency climbs, high-speed pursuits, or final attempts to escape overwhelming enemy numbers. Mechanical failure at 25,000 feet over Germany signified capture or death with mathematical certainty. The mission briefing proceeded routinely until Colonel Zemke announced the tactical modification. The 56th Fighter Group would escort B-24 Liberators to Brunswick, flying 300 miles deep into German territory where the Luftwaffe stationed its most seasoned pilots and most advanced fighters. The orders changed everything that day. No more careful fuel conservation like they'd practiced before. Now the pilots had permission, direct orders actually, to push the throttles wide open and engage the water injection whenever the tactical situation demanded maximum power. Johnson positioned Red Flight at 26,000 feet, 4 Thunderbolts holding loose formation while his eyes swept the crystalline sky above the bomber stream, searching for that telltale glint of metal that would signal German fighters incoming. Below them, the Liberators droned steadily eastward at 160 miles per hour. Their contrails stretched across the sky like white ribbons, visible to any enemy pilot within 50 miles. Staying alert meant everything. These escort pilots had to be ready to shift from formation flying to full combat mode in heartbeats. They needed to see the threat coming and react instantly. The Germans came at 11:47, exactly as textbook German tactics dictated. 20 Focke-Wulf 190s dropped out of the sun from 30,000 feet, using altitude and surprise to gain the overwhelming advantage they needed. Their BMW 801 radial engines, producing 1,700 horsepower each, gave them a performance edge they'd enjoyed throughout every previous engagement against standard Thunderbolts. Johnson didn't hesitate. He rolled inverted and pulled through a split S maneuver that pointed his aircraft directly at the attacking formation. At 25,000 feet, with his airspeed climbing through 300 miles per hour, his hand found the water injection switch. For 3 weeks, that switch had been disconnected, a safety measure after the March disasters when the wrong mixture had destroyed engines. This time, something different flowed through the supercharger. Methanol and distilled water, not the isopropyl alcohol that had caused those catastrophic failures. The change was immediate and absolutely violent. The R2800 engine, which had been producing 2,000 horsepower, suddenly exploded with power. 2,800 horsepower, roaring like controlled thunder through the fuselage. His Thunderbolt accelerated like nothing he'd ever felt. That massive bulk that usually felt sluggish in combat suddenly came alive. Manifold pressure climbed to 68 inches of mercury. Engine temperature stayed normal. RPM increased to 2,800 without a single mechanical complaint. Within 30 seconds, everything reversed. Where Germans had held the advantage in climb and acceleration, Johnson now possessed superior performance in every regime of flight. He pulled into a climbing turn that would have been suicide with standard power settings, and suddenly he was above the Focke-Wulfs despite their altitude advantage. The physics of aerial combat had just changed. German pilots accustomed to American fighters that climbed reluctantly and accelerated sluggishly suddenly found themselves facing opponents that could outrun and outclimb them. The BMW 801 engines now produced 400 fewer horsepower than Johnson's modified R2800. His convergence angles were impossible by any previous standard. His closing speed exceeded anything these German pilots had experienced before. The 650 caliber machine guns concentrated their fire into a target that simply dissolved under armor-piercing and incendiary rounds, traveling 2,800 feet per second. The German aircraft came apart in a flash of orange flame and black smoke. The pilot never got a chance to evade or even fire back. Johnson pulled through a vertical climb that gained 3,000 feet in less than 30 seconds, then rolled to attack the formation's second element. His wingmen, flying identical aircraft with identical modifications, were experiencing the same transformation. Lieutenant Eugene Roberts destroyed 2 Focke-Wulfs during a high-speed dive that reached 560 miles per hour, faster than any German fighter could manage in level flight. Captain Gerald Johnson climbed vertically through the German formation, using his superior power-to-weight ratio to position for deflection shots that had been impossible with conventional performance. The entire engagement lasted 18 minutes. When it ended, the 56th Fighter Group had destroyed 11 German fighters without losing a single aircraft. Complete tactical reversal. German pilots who'd learned to exploit American weaknesses suddenly faced opponents that controlled everything. Major Hermann Graf, commanding the German formation, sent a combat report that reached Luftwaffe headquarters within hours. His message was clear. American fighters demonstrated impossible performance characteristics. P-47s were climbing and accelerating beyond known specifications. He recommended immediate investigation of enemy technical modifications. His description of Thunderbolts that could outrun Focke-Wulfs and outclimb Messerschmitts was dismissed at first. Just combat exaggeration, they thought. But Johnson's post-flight debriefing documented everything with precision that satisfied both engineers and tacticians. Water injection had functioned perfectly throughout the engagement, providing emergency power whenever he needed it without mechanical problems. Engine temperatures remained normal. Performance exceeded every prediction. That methanol-water mixture had transformed the P-47 from a defensive interceptor into an offensive weapon that could impose its will on any opponent. Frank Walker's chemistry had been validated in the ultimate laboratory, aerial combat, where theoretical calculations translated into victory or defeat, survival or death. The transformation of the 8th Air Force began with a single teletype message transmitted from RAF Steeple Morden at 2100 hours on April 8th. Colonel Zemke's combat report, classified secret and marked for immediate distribution, contained performance data that contradicted every assumption about American fighter capability. P-47s had achieved climb rates of 3,800 feet per minute. Top speeds had reached 470 miles per hour at altitude. Most significantly, not a single engine had failed during maximum power operations that would have been catastrophic with the original injection system. Within 48 hours, mechanics at Debden, Boxted, and Leiston quietly began implementing Walker's methanol mixture, despite the absence of official authorization. Technical sergeants who'd witnessed months of engine failures suddenly found themselves installing a system that worked exactly as advertised. The underground network of maintenance personnel shared information through channels that bypassed normal command structure, driven by combat necessity rather than bureaucratic approval. Lieutenant Colonel Don Blakesley, commanding the 4th Fighter Group at Debden, authorized conversion of his entire P-51 Mustang squadron after consulting with engineers who'd studied the chemical differences between alcohols. The Packard-built Merlin engines required different injection pressures and timing, but the fundamental chemistry remained identical. Methanol prevented detonation, while water absorbed combustion heat, allowing manifold pressures that would destroy engines using conventional fuels. By May 1st, every American fighter squadron in England was using Walker's mixture. The results transformed aerial warfare. American fighter losses decreased by 37%. German fighter losses increased by 52%. Mission abort rates due to mechanical failure dropped to near zero. Most dramatically, the tactical balance in European skies shifted decisively toward American forces for the first time since the daylight bombing campaign began. The Luftwaffe recognized the magnitude of the transformation. Major General Adolf Galland, commanding German fighter forces, issued emergency tactical bulletins warning his pilots that American fighters had been fundamentally upgraded. The performance characteristics that German pilots had learned to exploit no longer applied. P-47s could no longer be outrun by diving away. P-51s could no longer be escaped by climbing to altitude. American fighters had become predators instead of prey. Frank Walker received recognition through channels he'd never imagined. Lieutenant General Karl Spaatz, commanding all American air forces in Europe, personally reviewed the combat data and authorized immediate implementation of Walker's system throughout the theater. The junior engineer whose laboratory work had been dismissed by senior experts found himself summoned to Patterson Field for consultation with the Army Air Force's highest leadership. Technical validation came through exhaustive testing that confirmed Walker's molecular theory. The Chemical Warfare Service analyzed fuel samples from combat aircraft and discovered that methanol maintained its anti-detonation properties under conditions that degraded isopropyl alcohol into compounds that promoted spontaneous ignition. Water injection, instead of being a desperate expedient, was actually superior to purely chemical solutions because it addressed both detonation and thermal management simultaneously. Production facilities throughout the United States began manufacturing methanol water injection systems using Walker's specifications. The Pratt & Whitney plant in East Hartford converted an entire production line to mixing equipment that could produce 10,000 gallons per day. Shell Oil Corporation developed storage and transportation procedures that maintained the precise 50-50 ratio essential for optimal performance. By summer, the mixture that had been assembled in secret by English mechanics was flowing through official supply channels to every American airbase in the European theater. The tactical implications extended far beyond individual aircraft performance. American bomber formations, previously limited to altitudes where fighter escorts could provide effective protection, began operating at 35,000 feet, where German interceptors struggled to maintain combat effectiveness. Deep penetration missions that had required massive fighter support could now be conducted with smaller escort forces that possessed overwhelming individual superiority. German technical intelligence captured damaged American aircraft and discovered the injection system that was transforming aerial combat. Their analysis revealed sophisticated engineering that had somehow solved the fundamental problem of extracting additional power from air-cooled engines without catastrophic failure. Within months, German manufacturers were developing their own methanol water systems, designated MW50 for installation in Focke-Wulf 190s and Messerschmitt 109s. But German implementation came too late to affect the war's outcome. American production advantages had already established air superiority through numbers, and Walker's chemistry had created technological superiority that German manufacturing could not overcome. By the time German fighters received their own injection systems, American forces were operating from captured airfields in France and preparing for the final assault on German industrial targets. Walker's discovery was measured in human lives saved rather than lost. American pilot casualties dropped precipitously as their aircraft gained the performance margins necessary to dictate combat engagement terms. German pilot losses increased as their tactical advantages disappeared. The aerial war that had been characterized by mutual attrition became systematic destruction of German air power through technological superiority combined with industrial capacity. Walker himself returned to the Pratt & Whitney laboratories in Connecticut, where he continued developing combustion chemistry that would power the next generation of American aircraft. His wartime breakthrough became the foundation for turbine engine development, rocket propulsion research, and ultimately the chemical systems that would power spacecraft to the moon. The methanol water injection that saved American fighters in 1944 evolved into the cryogenic fuel systems that defined the space age. The final irony was discovered in German technical documents captured after the war's end. Luftwaffe engineers had understood the theoretical basis for alcohol injection years before American implementation, but their conservative approach to combat modifications had prevented field testing. German expertise in chemistry and metallurgy might have produced superior results if applied with the same desperate urgency that characterized American development. Instead, their methodical approach to technical validation was overwhelmed by Walker's willingness to implement unproven theories under combat conditions. The laws of physics had not been defied. They had been revealed by a junior engineer whose laboratory work transformed the fundamental equation of aerial warfare.